So thank you very much for the invitation. Thank you to the organizers, to Cesare for the invitation, and to Stefan for all the organization. I am Lorenzo Monacelli from Sapienza University of Rome, and this talk will be about quantum simulation of ions, as the talk says. And in the very first part of the talk, I will try to convince you why it is important to do quantum simulations, and of ion in particular. And then we will see some more frontier results on non-equilibrium dynamics of ion, quantum dynamics, and particularly on a very interesting system, which is strontium titanate. You heard something about this system yesterday. I will talk about non-equilibrium properties of this system, what happens when we pump light in a very strong fashion inside this sample, and what can simulation tell us in this non-equilibrium regime. And then in the very last part of the talk, I will try to do some introduction to a topic that we are currently working right now, so it's a very work in progress, and is to find a way to perform simulation of electrons and ions within the same framework, so breaking down the Born-Oppenheimer approximation and going to fully non-adiabatic systems. So why it is very important to perform simulations of ions? And the main reason is that most of the properties of solids that you have actually depend on phonons, on lattice vibrations. And the reason is quite simple. It's because the energy excitation of phonons is comparable with room temperature. So this means that when you change temperature by a bit, usually what actually happens in a solid is that you change the occupation number of the phonons, so you are exciting effectively phonons, and this excitation interacts with the other excitation in the systems and change the thermodynamic properties. So most of the well-known thermodynamic properties of solids are actually an effect of phonon excitations. And so it's very interesting to study phonons for this reason, because if you want to describe thermodynamics and properties of solids, we really need an accurate description of the lattice vibrations. So atoms, lattice vibration came out from a competition in energy between potential energy, kinetic energy, and entropy of the ions. So by looking at the potential energy, we want to minimize the potential energy. And so this means that it is convenient to keep the ions fixed in their minimum of the potential energy. But this is detrimental for entropy and kinetic energy. So if you have a finite temperature, what the system wants is to minimize the free energy. And so you immediately see if the temperature is not zero, there is an extra contribution to the internal energy, which is entropy. And entropy usually wants to spread the probability distribution of your ions. So the larger the probability distribution, the higher the entropy. So the higher the temperature, the higher this contribution wants to be. So temperature tends to increase vibration for this reason. But even if the temperature is zero, so we are at 0 Kelvin, we still have vibration. And these are a result of the Heisenberg uncertainty principle. In fact, you can clearly see that if we localize too much the ions around the minimum of their position, we have an uncertainty on the velocity of the ions, on the momentum. And then there is the kinetic energy contribution, which is proportional to the square of the momentum. So if we have a high uncertainty on the momentum, this means very high kinetic energy. And so the system actually prefers to spread the probability distribution of ions, even at 0 Kelvin, to decrease the contribution of the kinetic energy. Now, the most used tool to study phonons in computer simulation is the harmonic approximation. And this is a very simple thing we can do. So we can take the potential energy landscape of ions. Here we assume Born-Oppenheimer approximation, so electrons stays in their ground state. And we can expand the potential energy of ions around the minimum up to quadratic order. We get a harmonic Hamiltonian. And since we know from our bachelor courses that we can solve the quantum Hamiltonian at any temperature, because we know the full statistical mechanics of harmonic Hamiltonian, we get all equilibrium properties of the solids using this expansion up to second order. And so in this way, we can compute essentially the partition function, and from there, free energy and all the derivatives like heat capacity and all the properties that we actually want. However, there are a lot of cases in which the harmonic approximation fails dramatically. And the first one is a very interesting one is the fact that harmonic approximation cannot describe the thermal expansion of the materials. And now all the materials, when you heat them up, you know that the volume change, and this effect goes beyond harmonic approximation, because if you have a perfectly harmonic system, you expand the volume, the springs that connects your balls of the solids will just expand, but the frequency will not change. And so this means nothing change in the harmonic properties of the system, and so you don't have actually thermal expansion in a perfectly harmonic solid. So to explain thermal expansion, we must go beyond the harmonic theory. And the same is true for most of the other properties that are written here. So if we want to describe second-order phase transition, or in general structural phase transition in materials, we need to go beyond the harmonic approximation. And when we have phonons and vibration that depends on temperature, this is usually an effect that comes from an harmonicity. And when phonons have a finite lifetime, they can acquire finite lifetime, and this is, for example, very important in thermal transport, and also in systems that display an anomalous isotope effect. And I'm going to show you one very easy example, which is the rock salt palladium hydride. Now, this system is stable at ambient pressure, and it is a superconductor, which is very well studied because of a very interesting properties, is the fact that this system has a superconductive critical temperature which show an inverse isotope effect. So the standard BCS theory predicts that if you increase the mass of your system, your frequency decreases, and then the superconductive critical temperature decreases as well. And now this material, if you replace hydrogen with deuterium, the critical temperature increases. So it's very peculiar. It seems a breakdown of the BCS theory, and so it was very well attracted a lot of attention for this reason. And this is a strongly anharmonic material, which you can see that the harmonic theory fails dramatically in this system, because if you plot, for example, the dispersion that you can compute from harmonic phonons, you immediately see two big problems. First problem is you see that there is like a charge density wave, which is this acoustic phonon mode that becomes imaginary in a very small region, and this is a signature of instability of the structure. So density functional theory predicts this system to be unstable. We know from experiment that that is not true. The system is stable. And then if you look to the spectroscopy measurement that we have of the phonon are gamma, so the experimental point is that very small point here, and while what is predicted by the theory is 5 times lower. So is an error of a factor of 5 that we have from DFT calculations. And if we replace hydrogen with deuterium, now it's possible experimentally to do all the dispersion, because hydrogen doesn't interact very poorly with X-rays, so it's very difficult to do this experiment with hydrogen. And you still see that these phonon bands, you still see here, for example, this is really clearly a breakdown of the theory, and also the higher bands. And even if you substitute deuterium with tritium, still the discrepancy is quite remarkable. So to describe systems like these, we need to go beyond the harmonic theory. And how can we do that? And so our approach was to employ this new technique. Now it's no more new, it's 10 years we developed this theory, which is called the self-consistent harmonic approximation, self-consistent harmonic theory. The idea is that we want to describe the thermodynamics of solids. So we want the free energy of the system. So we need a way to approximate the free energy of a anharmonic material. And now the approach is to rely on the Gibbs-Bogoliubov variational principle for the free energy, which states that the exact free energy of a system can be obtained by minimizing a free energy functional of a trial density matrix. So if we take a trial density matrix and we compute the average energy of that system, so we average the real Hamiltonian on the system on that density matrix minus temperature, the entropy of that density matrix. So by minimizing with respect to the density matrix this object, we obtain the exact free energy. Now this is exact, and the approximation relies on restricting the possible space of all possible density matrices. And the idea is to restrict these to density matrices which are solution to the most general harmonic Hamiltonian. And this is very similar to density functional theory, but for phonons. So essentially, we map the interactive problem of interacting phonons into phonons that do not interact and satisfy an auxiliary, fake somehow, harmonic system. And so this auxiliary harmonic system depends on two parameters, essentially, which are the average position of the ions and how much ion fluctuates, so the effective phonons in this system. And then by minimizing, with respect to these two parameters, the free energy and the anharmonicity is contained by the fact that the free energy is computed on the fully anharmonic Hamiltonian, we get an expression for the free energy. Now, you can see an example of the comparison between harmonic theory and self-consistent harmonic approximation in this double well potential. So this is a strongly anharmonic case of a double well potential. In red, you see the result of the harmonic theory. So what is? We find the minimum of the potential, then we expand up to second order, and we solve the ground state of the harmonic approximation, which is this Gaussian wave function here. Now, we can take this wave function and say, okay, we can use this to minimize the free energy of the system. And if we perform this, we end up with this green line, while the exacta, if we solve numerically this potential, we get this black line here, which is the exact solution. So this is more or less how the method works in a simple one-dimensional case. Now, we can apply this to palladium hydride and look what looks like. So we immediately see we can compute phonons from the effective phonons inside the theory, which is a bit like computing the band structure from effective band structure we get from density functional theory. And what immediately notice is that the agreement with the experiment on the phonons is restored, is much better. And also, we can see the difference of the prediction of the superconductive critical temperature using the harmonic approximation, which indeed shows us the standard isotopic effect. While using the self-consistent harmonic approximation, we saw this inverse isotope effect, and then it is much closer in agreement with the experiment. So the agreement is not perfect, because, and then this is a work in process, this material is very interesting and seems to have nonlinear properties also in the electron-phonon calculation, which are required to improve the agreement even further with the experiment, but this is not the topic of this talk. And so let me present another case in which quantum anharmonic effect on ions are really relevant and really impressive, that are when we want to, for example, compute the phase diagram of hydrogen at high pressure. This is a very interesting problem because hydrogen is predicted to become a high-pressure superconductor, and in particular a room temperature superconductor. Now, this prediction was done in the 60s by Ashcroft, and however, it is extremely challenging to synthesize pure hydrogen at a very high pressure, and it is even very difficult to analyze this sample experimentally because it does not interact with most of the probes we have that works at high pressure. So we really need to rely to characterize the phase diagram of indirect measurement, like how the Raman spectrum change when we change pressure, or how reflectivity of the sample changes when we change pressure, so which are very indirect way of measuring the structure of this system. And so we need the theoretical simulation in this case to somehow shed light on what are the possible phases, the possible structure candidates, and then comparing them with the experimental data that we have to see if we guess correctly. Now, to compute the phase diagram, theoretically, means to find a phase that minimizes, since we are at high pressure, at constant pressure, the Gibbs free energy, which is the Helmholtz free energy plus pressure and volume. And now, these are few candidates which have been identified mainly by the work of Chris Pickard in the past years. And here you can see that the big balls in the center are the average position of ions, while the small dots represent the quantum fluctuations of ions at 0 Kelvin. So these are snapshots extracted from the quantum simulation of actually where the ions are even at 0 Kelvin. So you can see that the quantum fluctuation in this system are really sizable, are comparable with the bonding distance. And so you can imagine that a system that fluctuates so much, an harmonic effect are going to be extremely relevant. And if we compute the phase diagram, now you can see Here I compare on the left side the hydrogen and on the right side the deuterium at 3 different levels of theory. So on the top we have the static phase diagram, which means we don't have any phonons at all, just ions are in their minimum position of the Born-Oppenheimer energy landscape. And you see that this is we predict hydrogen to go between phase 3 and phase 4, which are 2 molecular non-superconducting phase, and the atomic phase, which is the gas high temperature superconductor, is not stable before a terapascal, so completely unreachable from experimentally point of view. If we add phonons in harmonic theory, everything changed completely, and this phase 6 disappears from the phase diagram, and we directly pass between phase 3 to the atomic phase at a pressure which is very high, so half terapascal mostly, but reachable from experimental point of view. When we switch on an harmonicity, the phase diagram change again qualitatively. Phase 6 appears stable in a wide region of pressure. It's 160 gigapascal, so not negligible at all. And hydrogen is, the atomic phase is pushed toward higher pressure, so very difficult to reach, probably reachable in the future, not in the next 10 years probably. And the very nice thing is that we can do the same with deuterium, and we see an isotope shift of this transition. And the nice thing is that 6 months after we published this paper, an experimental work measured this isotope shift to be of exactly 30 gigapascal, so in very close agreement to what we predicted here. And so now this is how we can perform simulation of equilibrium properties. So this material roll in equilibrium, and we are studying small perturbation like experimental probe that probes small perturbation around equilibrium. But we can do more. We can try to see what happens when we perturb a system and completely alter its states. And this is require non-equilibrium quantum dynamics of nuclei. And this is very interesting because in the past years, experiments were capable of inducing exotic phase inside non-equilibrium state inside materials. And for example, they were capable of switching magnetic state in systems, induce a polar state in non-polar materials, alter and melt the charge order, and even there are claims, now this is very debated, but there are a lot of very interesting data on this part, to induce a superconductive behavior in non-superconductive material dynamically. So it's a very interesting topic. And as you can imagine, there is a lot of work to understand what's going on in this material. So it seems most of these claims seems very counterintuitive. And so we need a way to theoretically understand exactly what's going on, and some way for 2 reasons. One, for understanding, for a general physical understanding of what's going on. And the second reason is we want actually to be able to predict this phenomena to occur in new materials. And so we want first principle simulation, both to shed light on experiments and even to guide potentially experiments into discovering this phenomena in new materials. And so we are talking about experiments that work in the pump probe setup. Usually this means that we have a pump, so a very strong, usually laser pulse that interact with the material, brings the material out of equilibrium, and then we sample the same material after a variable time delay with a probe pulse that measure how some property has changed with respect to the equilibrium one, like how reflectivity has changed, how absorbance or whatever. And since we want to study lattice vibration, we will consider here the pump in resonance with lattice fluctuation. So we consider the pump in the mid-infrared or terahertz region. So it does not interact with electrons, but it directly excite the lattice vibration. And now the system I promised you at the beginning is strontium titanate. This system, as introduced also yesterday, is very interesting because it's a quantum paraelectric material. By quantum paraelectric, this means that if we look to these materials from a harmonic point of view, this would be a ferroelectric material. So harmonic theory predicts strontium titanate to be a ferroelectric. And if you look experimentally to the phonon mode that drives the ferroelectric instability, it goes down with temperature following the Curie law, But then at a certain point, it deviates from the Curie law and saturates, never reaching 0. And when this reaches 0, we have the ferroelectric transition. So this material never reaches the ferroelectric transition, but saturates. And this saturation is given by the fact that quantum fluctuation of the oxygen atom, in this case, stabilize the paraelectric phase. So there are multiple ways to stabilize a ferroelectric state in strontium titanate. One of these is strain. Another one is oxygen mass substitution. So if we replace oxygen with a heavier isotope, it does go into a ferroelectric state. And another one found in 2019 is to perturb the system with very strong electric field. So two independent experiments, one pumping the soft ferroelectric mode in the terrace region, the other one pumping the highest infrared active mode in the mid-IR region, displays that this system shows a spontaneous breaking of the inversion symmetry by measuring the transient second harmonic signal. And so this is an indication that the system underwent into a ferroelectric transition. Okay? And this is very strange if you think, because usually if you give energy to a system, you expect it to heat, and so you expect it to disorder. In this case, we are giving energy to a system, and then it's ordering. So it's transitioning from a paraelectric to a ferroelectric state. So it's very interesting, in my opinion, because it's clearly a non-thermal effect, this one here. And so how can we perform a simulation to understand why this is happening? And now this is very challenging because here we need the real quantum dynamics of this material. And so we need, in principle, to solve the time-dependent Schrödinger equation for the nuclei. And we need the quantum because this material is a quantum paraelectric. So if we neglect the quantum fluctuation, we will get a ferroelectric anyway, because it's quantum fluctuation that stabilizes the paraelectric phase in the first place. So this is really challenging as a problem. And so we cannot use classical molecular dynamics, for example. And to solve this problem, we expanded the theory I presented you before. We expanded the self-consistent harmonic approximation. And like for electrons, when we want to describe time dependency, we need to do time-dependent DFT. And we thought about why don't we introduce the time-dependent self-consistent harmonic approximation. And so what is the idea? So the self-consistent harmonic approximation essentially is doing a Gaussian ansatz for the density matrix, so which is the solution of the harmonic Hamiltonian. And so we can say, okay, we can keep the Gaussian ansatz also for the time-dependent wave function, and then find what are the equation of motion of this parameter that minimize the Dirac quantum action, so that we can get the equation of motion. And if we do like that, we can prove that the equation that minimize the Dirac action satisfy this self-consistent time-dependent Schrödinger equation, which, if you are a bit familiar with time-dependent DFT and time-dependent Hartree-Fock, is very similar. Now this is no more the real Hamiltonian, it's a self-consistent Hamiltonian that depends itself on the wave function, and it is an harmonic Hamiltonian. So we know how to solve this equation much more easy. Even if it's nonlinear, we know how to solve this equation much more easier than the exact one. And now this is an example. So I took the same double well potential as in the first example, and now I am applying a time-dependent electric field, which is swapping the two minima. And you can see in black here the exact time evolution of this system, and on red here what you get with the time-dependent self-consistent harmonic approximation. Indeed, the wave function in this case remains Gaussian because this is a constraint. But if you look, for example, to observable, time-dependent observable, like the average position of ions, you see that they describe very well what happens in the real case. Now, we implemented this for extended solids and applied on strontium titanate, and do the virtual experiment of pumping strontium titanate on the softest ferroelectric mode. And what happens is that even if our pump is in resonance only with this phonon here, and then if we do the Fourier transform of the motion of all ions, we see that actually all these other modes appear, so energy somehow transfer from the low frequency mode to high frequency mode. And this actually was also observed experimentally, that by pumping in resonance just with this mode, they saw appearing also higher energy mode in the X-ray diffraction spectrum. So this means that energy is actually transferred from low energy to high energy. This is very counterintuitive. Usually you expect that high energy mode decays in low energy ones. Here is the opposite. Is you pump so much that the energy goes up in frequency. And we also performed the simulation with a mid-infrared pump, so which was to reproduce one of the two experiments as I showed you before. And actually, we pumped with this electric field here in the same energy scale of the experiment. And what happens is that after 4 picoseconds, more or less, our system shows a spontaneous transition into a ferroelectric state. So you see that this is the ferroelectric mode. You see that after 4 picoseconds, it spontaneously goes into a ferroelectric state and remains there for a long time. And the same time, what happens is that if you look to the quantum fluctuation of the oxygen atoms, especially in that direction, we observe a drop exactly in that time scale, and then this is the antiferroelectric mode, and instead goes up in fluctuation. And the very interesting part is that this seems like the laser is somehow classicizing our system. So it's making the quantum fluctuation to collapse. And so since the quantum fluctuation collapse, the system is more classical somehow, and then it falls into one of the ferroelectric state. Now we did also a study as a function of the intensity, and we see this is an effect that can be switched on and off with so if we don't pump with sufficient enough energy, we don't see nothing happens. So this is a highly non-linear response. So we need, it's like a threshold effect. We need a sufficiently high electric field in the pump, otherwise the system does not do anything. And here is a small video, I hope you can see it, of the quantum dynamics. So here you see the system which has been pumped, and here is the quantum distribution of the oxygen atoms, and which are the largest one. Here is the titanium atoms, and you can see that when the system goes into the ferroelectric state, there is this squeeze of the quantum fluctuation of oxygen along the polarization, the induced polarization. Now, in the very last part of the talk, I want just to discuss briefly what is missing and what is the next state. So up to now, everything I talked to was relying on the Born-Oppenheimer approximation. So we actually have separated the electronic problem and the ionic problem. And so we treat usually electrons in a mean field, like density functional theory, and then we do complex stuff with ions to simulate their dynamics. However, there are a lot of scenarios in which we know clearly that the Born-Oppenheimer approximation failed. And one of them is if our ultrafast dynamics, for example, crosses a conical intersection. And so this is a phenomenon that's particularly interesting for out-of-equilibrium physics. But even in equilibrium, for example, if we have a metal that has a very low Fermi velocity, we know that this can violate in a significant part of the Brillouin zone, the Born-Oppenheimer approximation, and we get non-adiabatic effect. And this may be very important in material with low Fermi velocity, which usually means that we have flat bands, which usually means that we have very high density of state, which usually means very high superconductive critical temperature. So this is very interesting also for superconductivity and very relevant. And then when we have materials where there are very high energetic phonons, like hydrogen or carbon-rich materials, which have very strong bonds. Now, we need a way to go beyond. Now, there are multiple ways, some discussed also yesterday, to go beyond the harmonic approximation, the adiabatic approximation. However, I want to tackle a completely new way. So why cannot we use the same method we use to study ions to also study electrons? And so to treat everything within one framework. Now, this seems a very bad idea because electrons are very different from ions. And we know, for example, that while ions usually are localized in the lattice sites, and so using a Gaussian approximation for their wave function works very well, electrons are delocalized. In a metals, they have a wave function which are like plane waves. So we need a way to go beyond the Gaussian approximation if we want to describe electrons in this way. And the other one, that is even probably more crucial, is that electrons have very important exchange interaction, while ions usually exchange interaction is negligible. And so we need a way to introduce in the self-consistent harmonic theory to go beyond the Gaussian ansatz and to introduce the Fermi-Dirac statistic, essentially. So these are the major limitations that hampers the direct application of this theory to electrons. Can we do something in that sense? And the answer is yes. Here, machine learning comes into our aid, and we can apply actually a nonlinear transformation to our wave function to alter its properties. And so the idea is, okay, we can have a Gaussian in an auxiliary space, and then define a nonlinear transformation between the coordinates in this auxiliary space and the coordinates in real space. And this transformation alters our wave function looks like. And so I can give you a quick example. So if we take a transformation like this, very ugly, what happens is that by changing one of the parameters, like the z in this equation, we are actually changing the Gaussian into something which is not a Gaussian anymore. And the nice thing is that we can stack multiple transformations one after the other, and this is actually a neural network. And so how does this method work, essentially? So now we have a lot of parameters, because we have the parameters of our Gaussian in the auxiliary base. Then we have the parameters of the neural network that performs this map. Now, the idea is to do an unsupervised training of the neural network, which is we want actually to minimize the target energy of the system. And now this wave function is actually obtained as the wave function in the auxiliary space with the change of coordinate, plus the Jacobian, the determinant of the Jacobian of the transformation. And if you are familiar with variation at Monte Carlo, this transformation here resembles a bit a backflow, while this is very similar to a just throw. So actually, this is very similar to variation at Monte Carlo. And the other very nice thing is that one of the key properties of the self-consistent harmonic theory is that we have analytical entropy. So this means we can compute free energy directly without any thermodynamic integration. It's very quick. We don't want to lose this property. But thankfully, if the transformation is invertible, then we can prove that the entropy in the auxiliary space and in the real space is exactly the same. And so we preserve all the very good aspects of this theory. Now let me go to some results. And here is what happens in a double well potential. Here in red is the self-consistent harmonic theory. In black, the exact solution. Now we apply one layer of transformation. Okay, gets a bit better. 2 layers, 3 layers, and as you can see, the more expressive the nonlinear transformation gets, the closer we get to the exact results. And so here is how the energy change with the number of layers we introduce, which converge exponentially. And so we can go beyond Gaussian 1. Now, let's see how does it perform this with electrons. Here is the hydrogen atom, so very simple system. We know the solution analytically. But the problem is that the hydrogen atom has an electron-ion cusp. Okay, Gaussian distribution cannot get electron-ion cusp. And so with this very simple transformation I showed you before, even with few layers, we do better and better, and we improve the quality of energy. Indeed, we would need an ad hoc transformation to tackle this, but this is a very good sign already. And last is, before closing, this is what happens in an interacting electronic system like H2. Here we are dissociating the H2 molecule, and you can see the exact results in this case compared with the results of the theory. So it works very well. And not only, this is something that came to me with a high surprise. Even in a strongly dissociated regime, this seems to get a very nice result. So this method seems to account for strong correlation, which is something that usually we struggle a lot into too. And also excited states, now in this case it's very simple because it's a different symmetry, so we can minimize the energy quite easily. Also this we get in a very good one. And this, to say something, this is restricting the spin symmetry to be satisfied in this case. And so this is how the wave function looks like. Here the ground state exact one in 2 different regions in dissociation. Here is the ground state one. And so here I come to my conclusion. And so we have a way to compute equilibrium property of ions even in an harmonic, strongly anharmonic system. And the code we developed to do that is open source and can be used by everyone at the website. We have now a way to simulate out of equilibrium and dynamical properties. Now, the code to do linear response dynamical properties, so like phonon spectrum and all these things, is again open source. The out of equilibrium one, we are refactoring it to make it look nicer, and will be coming very soon, I hope. And then this last part with fully non-adiabatic, able to tackle both electrons and ions in the same framework, is still in very development. Now this is the work that Luca Leoni is doing right now, and I'm very, very hopeful for the future. So thank you very much for your attention.